Okay, so first problem is the most stable conformations about the given molecule. So how to solve that? If we look at these molecules, then we find that all these three methyl groups, this one, and this one, all are above the flame. Above the flame. So this is the point we have to keep in mind during problem solve. Here you find that all three methyl group is above the plane. This one, above plane. And another point we have to keep in mind here, these two groups are axial. So we find these are axial. And in this molecule, we find that these two are below the plane and these are above the plane. It is not supposed to tell that below the plane, above the plane, but in different directions. So this option is not. Same thing here also. In these molecules, these two are on same side and these are opposite side. So this is it is going to not the option on. Here we find that these two molecules, sorry, not these three methyl groups, all are same side. Same side. So among these two molecules or among these two conformation, one will be the most stable. But here we find that two equatorial and one axial and one axial methyl group. And you all know that if there is a axial, it suffers from 1,3-diaxial interaction based on the substituents. So here we have two axial, here is one axial. As the axial substituents suffer from 1,3-diaxial interaction, so this will be the most stable conformation. So option C is the correct. If we go to the next molecules, again the most stable structure is that. So again we'll go through that. So if we see option 1, we find that OH is axial and this is equatorial, means these two on the same sides, because our in the mother structures these two are on the same side. So first we have to find where the two groups in projected in the same side. So our goal to find two same side substituent. Same side substituent. So look, these OH and these methyls are on different sides, opposite direction. So these are not. Here it is on the same side. Same side. So we'll take it into considerations. Again, we find that these are on opposite sides. Opposite sides. So these are not. Again, we find this is on same side. As this is on same side, so we have to now compare between C and E. If we find that here, that in option C, we draw the structure. So this is OH and this is methyl. And here we may have, or not we may have, we have these 1,3-diaxial interactions. 1,3-diaxial interactions, which is unfavorable. But if we look into these molecules, option A, so this is the OH and it is here we don't have, first of all, any diaxial interactions because these are substituted by oxygens. Rather, we can find some hydrogen bonding. So this is stabilized by H bonding. So option C and option A. So option A is going to the correct option. So option A is the most stable structure of this kind of molecules, because it's do not, first of all, it is stabilized by hydrogen bonding, and number of 2 point is that it's do not suffer from the 1,3-diaxial interactions as that is in option C. So, so our point is that, so you will have 4 options. With careful observations, you can eliminate 2 options from any questions. and you have rest 2. In rest 2, just you have to use your brain, and mostly time what happens, the answer is inside the question. So just you have to be careful and you have to be attentive and you have to be clear from some fundamental point of view. Then you can easily address the questions. Third, so what will be the order of X considering X is equal to pH, Cn and Mb? So this question already I have discussed during the just before problem. So here, if this group is X, then X have some 1,3 Daxial kind of unfavorable interaction. So if this X become very much bulkier, then the interaction or unfavorable interaction will be larger. Here X is given pH, so I am drawing the molecules with all given X. So this is pH. And here, so X is Cn. So Cn is linear, the molecule is exposed toward the outside. And here X is methyl. So this is the methyl. In all case, we have 1,3-diaxial kind of interactions. But as this group is projected linear, here the interaction is minimum. So minimum unfavorable interactions. And here this is the moderate. Moderate in the sense among these three, comparable is moderate. Moderate unfavorable interactions. And here, as this pH group is quite bulkier and it has some rotation around this CC bond, so due to that, it suffers from the higher unfavorable interactions. So the order of X will be pH, and then it will be methyl, and then it will be Cl. Next we see the correct order of stability of the following cyclohexanes. So this is quite interesting questions. So following means just I'm drawing the structure of cyclohexane. Let's say it is given the unsubstituted cyclohexane. So we'll discuss about its different forms. Means then I'm going into this. So let's start with that. Here I'm going to show how the cyclohexane two different chair-like structure flips. Now let's put the numbering. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So what is my goal? So I will make carbon 3 down and carbon 2 up. As a result, where it will be 1, 2, 3, 4 will be on the same line. So how to do that? This is very easy to do that. So I am doing this. So like what is going to happen, and the drawing is very much easier. So I didn't do any change in 4, 5, 6, 1. So whatever 4, 5, 6, 1, it was, I will draw as it is 1, 6, 5, 4. I didn't do any change in these directions. It was as it is. And then what happened? 1, 2, 3, 4 comes in the same line. So here I am going to put, this is the thing. So this is carbon 2 and this is carbon 3. Then what I'm going to do, then I'm again doing the same thing. I'm again making the carbon 3 down and the carbon 2 up. Again, I didn't do any change around 1654. So let's draw that as it was. So this is 1, this is 6, this is 5, and this is 4. So as a result, now 3 will, it was here, 3 will come to here, and 2 was here, 2 will go to this position. So 2 is here. Yes, 2 is here. So what we are getting? We are getting these things. So 2, 3. So this is called half chair. Half chair. And this is called twisted boat. Twisted boat. Then what will happen now? My this side is ready. Now I will follow this one. So my 4, 3, 4, 3, 2, 1 is ready. Then I am what I am doing. So just I just down the carbon number 5 and carbon number 6. So this one ready. And so my goal is that so 5, 4, 5, 6, 1 will be on the same line. Now look, they are on the same line. So this is 5 and this is 6. So then again I am going to down the carbon 5 and going to up the carbon 6. As a result, what we are going to get, I'm going to get this kind of things. Okay, so 1 will be here, 2 will be here, and 4 will be here. So it will be 3. This one is, sorry, this will be 5. This will be 6. This will be 4. And this will be 3. So now this set inverts. So among these, again, one three exists that I didn't show you. So one both forms exist. So this is how. So if you want to draw their energy structure, so this is the way. So this is the twisted boat, and this is the half chair. Again, this is one half chair. Half chair. Okay. So now I'm going to show the different version of two different book. Okay. So look, here is it is. Let's write here. Let's say this is this cyclohexanes, and this is this half chair. Means this is this one. This, and this. This is one half chair. Then the twisted boat come into action. Twisted boat. Again one half chair. This one, and again this is another conformation of chair. These are all. So here this axis is the energy axis, and this is the energy flow diagram that are on. So here we have to be careful among the name as well as the structure. If in the option the name is given, then we will follow this trend. That chair form is most stable. Then sorry, it will be opposite side. Then it is going to be twisted boat. After chair, we have twisted boat. Twisted boat. Then it is half chair. Also, you have to be careful about the structure. The which is called half chair, which is called twisted boat. The structure we have to remember. If structure is given, let's the structure has been given and asking that the what is the correct stability order, then it will be the options. This one, then it is going to the twisted boat. We know that how twisted boat is, and then it will be the half chair. This question is frequently asked at different competitive exam. Now here I am going to show you another things, that another form of twisted boat, that how people think at twisted boat. Here I am showing. So due to lack of space, let's do it there. We all know that this is the boat form. Look, if I put a pressure on this edge, then it is coming here. So basically what we are getting, so these things, it was here. Now this carbon bond in this position. So this carbon come here. So I put a pressure and the boat become twist. So this is the boat form, and this is the twisted boat form. Twisted boat form. So if it is given, this structure is equivalent to this structure. If I see this from different angle, this also looks like this. So this is also twisted boat. So we have to be careful, or we have to be very much informative about the structure, that we not only remember the name but also remember their proper structure. So we have these two kind of twisted boat. So due to lack of space, I cannot show one thing. In the next slide, again I am showing some different part. Though here is some questions, but here just I am with the continuation of my previous discussion, so I am showing it here. So another things I am going to show here. So we have the chair form, and we have this half chair. You all know that these are the half chair. Then we had the twisted boat here. This is twisted boat. Then the boat form will come here. Okay, let's make it some higher energy. The boat form will come here. So this is the boat form. Again, one twisted boat will come here. This is twisted boat from another side. So again, let's write it down. TB. Again, one half chair will be here. This will be this half chair. I just write because AC half chair, and again this is different conformation. So I am not drawing this. So this is another energy for diagram. So whatever is included will follow accordingly. Boat form, twisted boat form, half chair. This is energy. So the option is now going to be like that. Chair is the most stable. Then it's going to be the twisted boat. Now you understand that twisted boat can be in two forms. This one form, another form is this one. Yes. So this is another form, and then it is going to the boat form. So we have to remember twisted boat is more stable than the boat form. Then we have half chair. So chair form, twisted boat, then half chair. So this is the exact stability order. This question is asked. Again, I am telling this question asked in CSIR net and gate. Not asked, routinely asked many years experience. And we become confused between these two. Okay, so this is the proper discussion. I put my previous slide. Now I'm going to this. So this is very much interesting. So the most stable confirmations. Now let's convert it into here. We have to remember that things. All the substituents are on the same side. All the substituent in same side. In same side. Because there are many questions to chemistry, but my goal is in this class to show you how to address the questions. So I have to put all the groups same side. Let's do that. It is let 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. In 1, we have one tert-butyl group. In 4, we have this one. Because I have to be on the same side, that's why I have given this. In 3, I have one OH group. So this is the OH group. And again in 6, I have the one OH group that is in the same side. And look, there is a, we know that this bulky group is very much unstable at axial position. So this is unfavorable, not unfavorable, highly unfavorable. Highly unfavorable. If this flip means this kind of things, then this was axial. Now it's come to equatorial positions here, equatorial, and this is what equatorial. It is now going to be axial here, which is axial. So what we are getting in the next carbon, it will be equatorial. So this OH is equatorial, and here this is again going to be after flipping axial one. This one will be axial here. Okay, let's again it is axial. So again it is the same thing here. We notice it is the same thing. So here you find that this chair form is unstable. Chair form is unstable. Unstable. So let's try this for boat form. So these are the boat form. So in the boat form, you notice that this group is here and this group is here. Very high unfavorable interactions. Again, unfavorable. Here I didn't put the weights because I'm not considering that. So if I put the weights, so one weight will be here, another weight will be here. That I am not putting here. And then I have one option. I will go to the twisted boat form. The twisted boat form will be like that. So if this is the twisted boat form, so now look, this substrate is here, and this substrate will be here, and one weight will be here, and one weight will be this position. So see, these two groups are far apart from each other. These are far apart. So they suffer less steric hindrance. So less steric interactions. So we always should not remember that if it is given that SCR is the most stable form, that always the molecule will be stable at CR form. For the given case, this twisted boat form is the most stable form. So this is very much important question. So twisted boat will be most stable one. Okay, I hope you have got this problem. Later, okay, this is also interesting problem. The most stable conformations among these two are what? Normally, what happens if we have two different group? Let's say, uh, let's say generalize. Let's say it is X and it is Y. Then what happens? They are H. If two different group X and Y, mainly they are stable in staggered positions. Staggered positions due to a relaxation in dipolar repulsion, because one dipole will be this sides, depending on the substrate, one dipole will be this sides, as well as due to relaxation in steric interactions. Mainly it happens. So due to the relaxation in steric as well as in dipole interaction. Steric as well as in dipole interaction. Dipole interaction. But here we will not use that. Yes, something interesting point happens, particularly for these molecules. If I see here, one dipole exists in this form, and here one dipole exists in these directions, and this is H, this is H. Though dipole relaxation align in such a fashion in different two dihedral form angle, but yet let's draw this H group here. This is stabilized through H bonding. H bonding. So we have to consider this one. Due to this H bonding, this compound is stabilized. Though this dipole is here, though dipole is here, but this is unstable due to lack of hydrogen bonding. So this is the option. Yes, this is the most stable conformations. Next problem we'll see. This is another interesting problem. Okay. So look at these things. So normally, if you see that there is a relaxation of dipole interaction here, but it is not the case here. Two dipole exist this size. But yet another things here happens, particularly for these molecules. So let's draw it here. It is fluorine H, and this F, H, H. Another interesting phenomenon happens. This, so this is the sigma star of CF bond. Now, this siege bonds, the backside, siege bond on the backside, this one, siege bond present in staggered conformations, not staggered conformation, siege bond present in anti-periplanar positions. This is a more perfect term. Anti-periplanar positions. Delocalize into this CF sigma star. Delocalize into this CF sigma star orbital as they align parallelly. Due to this Gooch conformation is more stable. See the Gooch conformation. So we find that we always should not do that the anti will be stable. Here the Gooch conformation is more stable. And this particular effect, that is the delocalization of this siege bonding electron into the sigma star of CF, is called the very important name Gooch effect. This is called Gooch effect. We have to be careful when the problem is given. We have to look at the substituent. Then we can. Then another things, that is Gauss-Butane interaction. Okay. So we almost all about that. Let us visualize that. If we look at this methyl group, basically this is the Newman projections of butane. CH3, CH2, CH2, CH3. This is CH3, H, H, CH3, H, H. Now, these two methyl groups are present in Gauch conformation. In Gauch conformations. And we can clearly visualize that these two methyl groups in Gauch conformations, there is a interaction between these two methyl groups. And if you see that number carbon is 1, 2 is backside, let's say this is backside 2, front 1, 3, 4. We have total 4 carbon. We have total 4 carbon. So in the butane-like skeleton, in the Newman projection of butane-like skeleton in Gauch conformations. So it is in the Newman projection, what I am calling it is butane light, because here it is butane. Later I will show that if it is not butane, but considering 4 carbon, there will be interactions, mixed kind of thing. That I am telling. That's why in the Newman projection of butane-like system, let's configure that 4 carbon at Gauch conformations. So this is the what in the Newman projection on double in the Newman projection of butane-like systems at Gauch positions. One unfavorable interaction exists. One unfavorable interaction exists, and this is called Gauch butane interaction, as it is in Gauch positions and originate from 4 carbon system. This is called Gauch butane interaction. Gauch butane interaction. And it is unfavorable. If I show you the value, then you will also understand why I'm telling the unfavorable. If its staggered form will be this one, CH3, CH3, H, H. So this is the staggered form. This form is more stable than this form by 2 to 3 kilojoule per mole. So this is the energy. And this is unstable by this amount of energy. This is called Gauss-Butane interactions. It's the unfavorable resistance. So question, what is being asked? In the question, the examiner asked how many Gauss-Butane interactions, how many Gauss-Butane interactions or any Gauss-Butane interaction exist or not, or Gauss-Butane interaction, let's say int exist. They ask these questions. We have to, if we see this approach carefully, we can address for that. Okay. Now it is another interesting thing. So let's what to draw the Newman projection of following compounds. So I put these examples because so that we can learn this approach. Sometimes we become confused from which side to look, how to look. Here I'm trying to avoid these things here. I'll show how to look, but later I'll show without looking this we can solve this. So these are the things H and H. Look. So this frame is my ready. Which frame? This one. This. So let's put the number. Then like will be 0, 1, 2, 3, 4, 5, 6. So now I'm not doing any change around this one. So this is carbon 4, this is carbon 5, this is carbon 6. And one carbon 6, I have one hydrogen. Let's say this is the hydrogen. I marked it for references. So this is that hydrogen. Here at carbon 4, I have one hydrogen. Again, I'm not asking you to look any sides. Just I'm trying to the solving approach, how to do that. Here, this is hydrogen attached with 4. This is 4. And this one 5, 5, 6. And with 6, I think I have done some mistake. With 6, I have one hydrogen. Okay. So I have done one mistake here. So this will be the hydrogen. So this will be the hydrogen. Sorry for inconveniences. Yeah. So this is the hydrogen marked here. Now I put this one H and 6 is here H. Now look. So here just nothing. I have just cut out this and placed it here. Now I put the Newman projection circle in these two positions. So this is ready. Then what is my job? Then the connect one that is on back side. So here in the back side I have 1 and in the back side I have 3 here. So 3. So I have to connect 1 and 3. So how they're on the downside. So just here I am connecting 1 and 3. So this is the Newman projection. So without looking at any reaction. Now I will add the hydrogen as it is. So this is the hydrogen on back sides. This one, this is here, this is here, and this is here. Now I am adding. If you look through these positions, then you can also get the same thing. But here I have avoided the looking and I also have avoided the imaginations here. Okay. So what is our first goal? What we have done? Okay, let's show it some different places. So this is the projected cyclohexane. So what we have done, we have cut it. So this is first point. If we cut it, then we have this. Second point, add hydrogen. So we will add hydrogen here, means I have cut it, so hydrogen here and hydrogen is here, hydrogen is here. Cut is mean here I have cut one extra carbon, but stop it here. So just cut these positions, these and this, cut these two. We have cut these two, these one we have cut. Then we have added these two hydrogen, then add again these hydrogen, so add again these hydrogens. Then what is the put the circle, put circle. So we have put the circle here. Then what is number 4? Then join back carbon, join back carbon. So one is here, another is back is 3. I have joined that. So this is the easiest way to draw the Newman projection of cyclohexane without any imagination, without any looking. If we use this approach, we can address the question very easily, and there is a least probability that this will be mistake. So we'll use the same approach for this given problem. So now what we have to draw? So again, we have to draw the Newman projection. So we'll cut this frame. So cut the frame, lower side. If we cut the frame lower side, then what will have? Let's say let's put the numbering. If we put the numbering, then what will happen? Let's start it from here. Let's say it is 1, this is 2, this is 3, 4, then it will be 5. You know the nomenclature system. 6, it is 7, it is 8, it is 9, it is 10. Now I am cutting. Look what I am doing. This one. Okay. So this is carbon 3, this is carbon 4, this is carbon 10, this is carbon 5, this is carbon 6. So cut up to this. Now erase that. I'm just cut one extra carbon, that's why erase that. So this is 3, 4, 10, 5, 6. I have cut up to that and put the number in. 3, this is 4, this is 10, this is 5, this is 6. Then add hydrogen. So here we have hydrogen, here we have methyl. Let's put the methyl. It is ready. Then it is front carbon, we have hydrogen. This one means this hydrogen. So I have done this. Then see, just add hydrogen. So we have hydrogen at 10, 6 we have hydrogen. We have add the hydrogen. Then what? Put the circle. Step 3. Circle have put. So my part is ready. Then join the substituent. So joins backside is 7. Here we have 7, and it is 9. So this backside is 9. So join 7 and 9. There is on down positions. And also I can find that easily. This is carbon number 8. Look, this is carbon number 8. Then again add 9 and 2. Backside is 2. And this is 9. Then join 9 and 2. And we see that this is carbon number 1. So there is no matter of confusion also. This is carbon number 1. Then I will add the other substituent, says, and just I will add that. This is the very simple approach. If anything, any complex thing is given, you can easily do that. So this is the easiest approach to draw the Newman position. Here, if it is asked in this question, now it is ready. So how many gauge butane interaction is present in this molecule? Okay. So look, or are there any gauge butane interaction in the given molecule? It may be the answer. So look, this is methyl 1, backside 2, 3, 4. Here we can find 2 are in gauge position. So then we can find one gauge butane interaction is present. Right? Look at here. These systems. This is 1. carbon 1, 2, 3, 4. Here we can identify one Koch butane interaction. So in this question, the question is very much interesting. Why? This question can address two things. First one, the Newman projection of this kind of decalane systems with nomenclatures. We can easily address that. So Newman, and number two, it is interesting due to the fact that it can identify the Gauss butane interactions also. So this question is very much interesting and important for competitive exam like CSIR, NET and GATE. And if you look at the questions, just it will hardly take 1 minute to address that in a perfect option. Okay, let's come to the latter one. This is another problem. Which of the following reaction is faster? So basically, it's a SN2 type reaction. These sodium ethoxides with their sodium salt. So what happens? So let's add the substituent here. Then we can easily understand this. Is on substituent H. And here if I do that, this is H. Okay. And look. So let's come to here. ETO minus. They are in anti-periplanar. These two groups are anti-periplanar. Anti-periplanar. So E2O minus abstracts these protons and these go and this OIT leaves. As a result, we get these things here. But here, these are not in antiplanar. Not in antiperiplanar positions. As a result, it is very easier pathway for the reaction. So definitely this reaction will be faster because it is as expected conformation that of the E2 type of elimination. So this will be much more faster. Okay. Next problem. Now, what will be the product if NaBH4 reacts from rephase? Then our first one to consider what is called rephase. But this is the simple rule. So this is carbonyl is option 1. Then 2 will be here or here, but this is more priority as this carbon is attached to one methyl group. So this will be 3. We are finding 1 to 2 to 3. It is in clockwise. Clockwise means the phase, let's say methyl group is front side to you, means if you on your mobile, then methyl group projected to your towards you, and this ring is present on the ring. So this is clockwise, means this is a rephase. A rephase. So this phase is a rephase, means the phase you are seeing, that is the rephase. Opposite side of our skin is the psi phase. So this phase we are observed is this phase. So now the question is this: sodium borohydride will attack from rephase. Then what will be the product? So this is the methyl group. This is the hydrogen. So we know that this is a rephase. So it will attack hydride to have the same side that of the methyl. Rephase means hydride will attack from the same side that of methyl. If that happens, then we are going to get, this is methyl here, and this is, let's put the stereochemistry. We must have to put the stereochemistry here. Yeah. So this is, let's say I'm not putting O minus, rather it is OH, and this is the hydride. Because hydride means hydrogen and methyl will be on the same sides as the attack happens from the rephase. So this is the product that we're going to get. So if it is asked that what will be the product if the attack from Cypress? Cypress, if it is happen, so this then we can draw that Cypress means the opposite side. So opposite side means the hydride will come from the opposite side, that of the methyl group. So hydride will be here, and this will be the OH group, methyl and hydride. So this will be the product if the attack H minus attack from Cypress. From Cypress. This is another problem that's important for competitive exam. In my first classes, I discuss about this kind of systems, molecules. So the type of axis present in the given axis. If you want to see this, first of all, this molecule is achiral. Why this molecule is achiral? So these two groups are different, but these groups are same. So following that logic, it is achiral. Now you have to replace one hydrogen by some another group. Let's say Z is that group. So I replace one hydrogen by Z, which is other than hydrogen. Now these two groups are different and these two groups are different. So this is the chiral axis, not chiral, this is the chiral molecule. If it is chiral molecule, now this axis is the chiral. This is the chiral axis. And the previous version, so before chirality, is post stage of chirality. So this axis is pro-chiral axis. Pro-chiral axis. So the axis that is being asked that is pro-chiral in nature. Very simple questions. To the next part. Okay. This is very easy to solve. So which type of chirality exists in the given molecule? So it is very answer to say. So if you draw a plane in the molecules, let's say your screen is the plane. So in your screen, this is your font side, this is your font side. So both sides is different. So both side of the alkene group is different. This is in the same side, but it is the different. They have different kind of things. So it's a plane chirality. Answer it. Because it's like a handle. Means alkene one side is twisted in this kind of forms is there. So one side we have this, other side we don't have that. So plane chirality exists. Plane chirality. Because two different chemical environment on the both side of the plane. Two different chemical environment on the both side of the plane. Okay, so what to do if this is a plane chirality? Then we have to find the pilot atom. So pilot atom is first out of atom, out of plane atom. So this is on plane. So this is first out of plane atom. If this is on plane, so then this is the first out of plane atom. So if which is the first out of plane atom, so I am going to the make numbering. Here it will be 1. First out of plane atom, this is 1. So this is pilot atom. Pilot atom. If this is pilot atom, so this is going to 1. If it is 1 by default, this is 2. And this will be 3. Next thing. So 1, 2, 2 to 3, we find that it is clockwise. Clockwise. If this is clockwise, it is going to be R. And this is RP, means it contains plane chirality. Now this is the mirror image of this one. If this is that, so now this is the pilot atom here, because first out of plane atom on the preferred side means, so this is the preferred side, this one, that's why it is a pilot atom. Okay, so this is 1, this is 2, this is 3, and 1 to 2 to 3 here I find this is counterclockwise. This is counterclockwise. If it is in counterclockwise, then it is going to be SP. So which type of chirality exists? We got the answer. First of all, this is a plane chirality. And if this is plane chirality, then the left one is RP and right side one is SP. And for stereochemical property discussion, we have made the P. Another interesting problem. Yeah. Look. So what is the preferred configurations of the following molecules? So here we find this group is equatorial and this group is axial. So it normally comes to our mind that as it is in axial position, this is going to be the unfavorable interactions, but it's not always true. It depends on the substituent. So here first look, this is equatorial, but these hydrogen and these hydrogen suffer from 1,3 diaxial interaction with this methyl group. So this is 1,3 diaxial interactions. This is 1,3 diaxial interaction, so this is unstable. And here, once it flipped to different form, see no hydrogen here. And now these two hydrogen projected in the opposite sides. So there's no 1,3 diaxial, so no unfavorable interaction. Though this group is present axial. So this is the most stable conformation. Here these examples that one bulky group at axial position, yet this conformation is stable. So this is the most stable conformation. And this one is the most stable conformation. Highly interesting. That seeing it is the axial position, we may drop the answer to different side, but this is not. So today I'm finishing my class here. There are many points yet to discuss us about stereochemistry, but I will not discuss right now. I will stop all this discussion in my 3 class. Later in some different time, I will discuss. Next class, I will shift to the alkene part. Mainly, I will cover the book Carothers and some other books from the questions being asked, some problem from Nanj, and some problem from journal. I will cover all the things from next classes. Functionalization of alkene. This is very much important chapter from the next class. I will be keeping on discussing this class. It means first basics from Carothers we will discuss, some problem from Nanj, and some problem from CSIR net, get IIT exam, this kind of problem. This is my next target. Right now,